Okay, the other thing we're going to do today is we want to take a little time to basically review and make sure our first 3 weeks are down before we move forward. So here's the things we need to make sure of. In this week's lab is just build these. I tell you to draw schematics, big thing, draw the schematics. I don't remember if it's this class or one of the others, but I tell people the main draw the schematics. I want to start seeing you can draw them, and everybody skip drawing it, and apparently I wouldn't build it or something. I don't know. If I say draw it, draw it. So, in the lab. I'm not going to write everything down again, but I have you build a series circuit. I say, here's your 3 resistors, and here's your supply. I'm pretty sure I tell you 24 volts. And the little trainers can only go to 17. How do I get 24? These guys. Do not connect that power supply into this power supply or have this power supply connected to the board. When you do that, or you will burn up my equipment. Do not do that. If you want to, you can grab the other separate breadboards, but you can also just jump wires over here. I will also tell you, if it's this week or one of the next weeks, start using terminal strips. Every single station has these, and it's just a different way of connecting things. I want you to see a few, and this is a physical connection. You're not plugging little things in, and you're not soldering. These 2 pieces, this is just a solid piece of metal under there. So how do I connect things? I screw down the screw on one side to lead and screw down the screw on the other side to lead, and it's connected. And that way you can do different connections on here. It's, in a way, a more simple system, but I found that some people, their first time doing it, struggle just because it's different. So just ask. But it's just the 2 sides are connected. So if I want to run a resistor, I screw down here and here. You just back these screws up a little bit, and then there's a little flat plate underneath, and you can slide 2 leads under it easily, 1 on each side. And you can pretty easily squeeze a couple leads on one side and a couple on the other if you want to force it. And you just use a Phillips screwdriver to back them out and tighten them up. I don't remember if that's this week I tell you to do it, but I do a couple weeks. And that's only because part of your goal ought to be, I understand the difference in the physical, how I have to connect things, and how the electricity flows, how the current flows in there. So I can take different things. And we might even get at some point to, I don't know if we'll get a chance to do like crimped connectors and things like that. These work different. Car battery, you've seen those. You have a clamped on connector, and you just slip it over there and tighten it down. It's perfectly good physical connection. We have a lot of those for little higher power things that have a crimp on one, and you crimp down the wire, and then you can just drop it on and screw it down. A little different than our little pieces. Right. Anyhow, so wow, you're going to build a series circuit. You're going to go through again, and you're going to just solve all the math for it to make sure you're good. Hopefully, you're just like, this is going to be trivial. I'm just going to kick this out. And then I'm going to have you do the same thing with parallel. Same thing. Draw the circuit. Build it. Make sure you use the right power supply. And these are a little more free form. I just want you to go in and show, hey, I can build this whole thing up on my own and do it. And then I have a series parallel. So we did those last semester some. Series parallel was new, I think, last week for us. So I have one of these. I want you to solve the whole thing and then build the whole thing and test it and make sure all those voltages match up between the 2. That's it. I mean, that's our lab this week. It's going through that. Here's why, and here's where we're headed next. If you look at the core of this class, it's something called networking theorems. That might sound like it has to do with networking, like what we talk about in the modern world, and by modern, I mean like the last 40 years. But networking theorems in electronics have existed for 100 years. What they are, and I'll just give you a little bit look ahead of it, is we'll start talking this. We've done Kirchhoffs laws to say I can sum all the voltages and they have to be 0 in a loop. So here's a problem we can't solve right now that we'll work on later, maybe Thursday, but probably next week. So let's say this is 12 volts. 1 kilo ohm. That's 1.5 kilo ohms. That's 1.2 kilo ohms. And that's 15 volts. And I should be able to solve for all the voltages and current. So I can come in here and say battery 1, battery 2. So I have battery 1, battery 2, the 1 kilo ohm, 1.2 kilo ohm, 1.5 kilo ohm. How do I solve that? I'm going to ask you, actually, I'll go ahead and do it since we have a little time this morning. Voltage, current, power. How would you do that? Let's look at it a second. When you look at it. Any ideas? Is that a series or a parallel circuit or a series parallel circuit? The answer is well. Okay, so let's go ahead and do this today. We'll work on this. I don't think I have anything to do this week, but I need to start thinking about this. So let me remind you of Kirchhoffs laws before I go on. I'm going to put them over here. Do you remember Kirchhoffs laws?
Power in as power out.
So that says at a node, the current law, it's got two of them. The sum of all the current in equals the sum of all the current out. Yeah, we need that. So I look here. I have a node. I have a current that's going to flow here through this battery, through this resistor. I'm going to call that current 1. I'm going to have current that's going to flow here through this battery, through that resistor. I'll call this current 3 because in the middle I'm going to have a current that flows through this resistor. I'll call that current 2, right? That'll be all my currents in the circuit. So if I were to come over and use this, currents in, I could say, I1 plus I3 equals I2. Now I have two nodes. I have this node, and this node here says I2 would equal I1 plus I3, but that's the same equation. So I have two nodes, but really it give me two identical equations. So I could use that. Now the problem is I don't know any of those, so I use that means, well, I guess I'll start doing something with it, but I don't know what yet. Now, the other one, Kirchhoffs law, loops. And that says the sum of all the voltage. I do delta V, so the drops across each thing equals 0 as I go through the loop. Now I have 3 loops here. So I'm going to go through loop 1. Let's see if this will work. Maybe, I don't know. Loop 1 on the left. I'll start right here on the side of the battery. I go up 12 volts. Put a plus to make sure I know I gain voltage. As I go through a resistor, I drop voltage. So I'm going to drop the voltage across resistor 1 there. And what would be my voltage drop?
4.8.
And I don't really know it right now. What I know is the voltage drop is Ohm's law, so current times resistance. So I can take the current that flows through there, which is I1, times my 1 kilo ohm resistor. And then as I go on around my loop, I go from here to here. I'm going to drop across that resistor in the direction of current. I always drop. I would drop I2 times 1.5 kilo. And that would equal 0. That's that. Loop 2, I use the one on the right. I'll follow current direction again, and I assign the current here. If I assign the current the opposite direction, all my math would work as long as I did it right. I would just get negative numbers out, which would say, oh, current actually flows the other way. That will happen sometimes. I could set these batteries up so they fight in the center, and I won't know until the end which direction that middle one's actually going. Okay, so I go up 15 volts. Then I drop 1.2 times I3. And then I drop I2 times 1.5 ohms. Yeah, this is the same voltage. It's part of both loops because that center leg is shared. All right, now if I stop 1 second, I can look and I go, I have 3 unknowns, I1, I2, and I3. I have 3 independent equations. Algebra. I know how to solve 3 independent equations with 3 variables by doing solve for a variable and substitute. So it's tedious. That's what you have to do. But I'm going to note there's a third loop here. If I went around the outside, I could do that. I could start right here. I go up 12 volts. I drop I1 times 1 kilo ohm. I drop I3 times my 1.2 kilo ohm. No, I gain. Actually, I gain. See the direction of, and then I drop 15 volts. Because watch the direction. If I'm going from, sorry, what did I do wrong here? Oh, this is wrong. I drew my polarity here wrong. What the heck? Sorry about that. Did that for all these. You should be dropping across the resistors in the direction of current, because that's the direction it's going to drop. So I would go up, negative, positive. I would go down. I would go up, and then I go down. Now here's the thing. Those are 3 dependent equations. This one's dependent on these. Remember for algebra what dependent means? Just means if you try to solve these 3 equations, it won't solve because they aren't independent of each other. So I'm going to, I generally won't use this one. I'll ignore it. So I have 3 equations, 3 unknowns. How do I solve those? Much tedious algebra. And I don't have a better solution because you have to do it. You have to go ahead. So, oh wow, look at this thing. That's been sitting there all summer. Algebra. 3 equations, 3 unknowns. I'm going to write them all down here. So I1 plus I3 equals I2. I'm going to drop my units here because it's going to make it easier to do the algebra without carrying around those units all the time. Here's the thing, these are kiloohms. So I'm going to keep my resistors in kiloohms, my volts in volts. That means all my currents will end up being milliamps when I'm done. So, yeah, if I thought about it ahead of time, I would have used just ohms, so I didn't have to think about that. So I have minus 1 I1, so it's just I1. Minus 1.5 I2. And then down here I have 15 minus 1.2 I3 minus 1.5 I2 equals 0. So any idea how to solve there? You did the same thing. If you've done like algebra 2 or college algebra or anything, you did the same thing. So you used X, Y, Z instead of I1, I2, I3. You know, you did a bunch of where you did X and Y and had 2 equations, 2 unknowns, and solved for 1.
So So couldn't you, like, for the bottom two, make the very bottom equation times it by negative, and then use elimination, I think it's
Yeah, you can't get, here's the problem, right now I have all three variables in those two equations. So I will do that in a second. So I'm going to substitute, instead of substitute, I'm gonna substitute it. I2 equals I1 plus I3 in both of the other equations. So I'm going to take this equation, I'm going to say, hey, 12 minus I1 minus 1.5, I2 is equal to I1 plus I3. Then I multiply through and I get 12 minus I1 minus 1.5, I1 minus 1.5, I3 equals 0. And I add these two together. So now I have that one just in terms of I1 and I3. Then I'm going to take the other equation. I'm going to write 15 minus 1.2 I3 minus 1.5. And again, I2 is equal to I1 plus I3. .5 I1 minus 1.5 I3 equals 0. 15 minus 1.5 I1. 1.2 plus that's minus 2.7 I3. So now I have two equations with two unknowns. Just took substitution in. So I got rid of I2 of both equations. Now this is where I think you're headed, buddy. I can write these equations like this. 15 minus 1.5 I1 minus 2.7 I3 equals 0. 12 minus 2.5 I1 minus 1.5 I3 equals 0. Since I can do the same thing to both sides of an equation, I can multiply one equation by some handy-dandy number, so if I sum the equations, they would cancel a term out. All right, so I don't have anything that stands out here, so I'm going to just take this equation right here. I'm going to write it in parentheses, and I'm going to write some out here. 15 minus 1.5 I1 minus 2.7 I3, 0. I'm going to look here and say I'd like to make I1 be equal to plus 2.5. So how did I do that? So I multiply by minus 2.5 over 1.5, which seems like it ought to be 5/3, but it'll work out. So I multiply that here. So take 2.5, 1.5 times 15, and I get minus 25. Take this times 1.5, I get plus 2.5 I1. Take it times this. I get plus 4.5 I3, take it times 0, I get 0. So this is the same equation as that, right? I multiplied both, two equations, or two sides of the equation are exactly equal, so if I multiply both sides by exactly the same thing, it's okay. One side, two. Okay, why? Why did I do that? Well, I'm going to take that equation, minus 25, by the way, you can do this through tedious substitution, kind of like you did there, just do it again, but this is faster. Now I'm going to take this equation and write it down. I have two equations. Both sides of both equations are exactly equal, so I can do the same thing to both sides of both equations. So I can come in and I'm just going to take this entire equation and add it to that equation. I'm going to add the left side to the left side, the right side to the right side. Does this come back and ring a bell for what you did in algebra? Yeah. especially you guys who just had algebra a couple years ago. So, minus 25 plus 12 is minus 13. Plus 2.5 plus negative 2.5 is going to be 0. 4.5 minus 1.5 is going to be 3. Now I can move my 13 to the other side. I get I3 as 13 over 3 milliamps. 4.33 milliamps. Hey, I found I3. Cool. Now I'd like to go back and find one of the other currents. Well, I'll just take this equation up here. I'll take 12 minus 2.5 I1 minus 1.5, and I'll plug in I3, which I said, let's put the 13 thirds will probably be easiest to put in, equals 0. So 1.5 divided by 3 times 13 is 6.5. So I put 12 minus 2.5 I1 minus 6.5 equals 0. Take that to the other side, so I have 2.5 I1. 5.5. So I1 equals 5.5 over 2.5, which is 2.2 milliamps. And then finally, I know I1 and I know I3, and I2 is equal to the sum of them. So I2 is equal to I1 plus I3, which is just going to be added together, right? 4. So I get 6.53. So I solve for all 3 of my currents. That would let me find the voltages across each one of these, right? Just current times. So, I mean, we can go ahead and do that. So this is so I2 is through 1.5, that's my 6.53, right? 1.2 is my I3, which is 4.33. That's also the current through that battery, so 4.33. And let's see, the other current was 2.2 through this battery and this resistor. I've done the hard part. I can find the voltages now just by, well, that's 12 volts. That's 15 volts. All right, resistor 1's 1K times 2.2 is going to be 2.2 volts. 1.2 times 4.33 times 1.2 kilo is going to be 5.2 volts. 6.53333 current times a 1.5, 9.8 volts. Let's just check this. So we just got done saying this is 12 volts. This is 2.2 volts. This is 9.8 volts. It's getting cluttered up here, isn't it? But check my loop. I go up 12, I lose 2.2, so I have 12. Take 2.2 away. Take 9.8 away, I'm back to 0. So my loop works out perfect. My loop over here, I went up 15, I dropped 5.2, so 15 minus 5.2 leaves me at 9.8, I dropped here. So I just checked my loops, they worked out. Go to your power afterwards if you want. The power in by the 2 batteries ought to equal the power out by all 3 resistors, just like usual. And so that's using Kirchhoffs laws to solve these problems we couldn't do before. So those are the types of problems we're moving towards. So for this week, like I said, homework is mostly about meters and metering and how that works, just to keep you thinking about it. And then the lab itself is just a series and series parallel circuits, just working with some a little bit different equipment, but not a lot. I don't think it should be too bad. So, questions on things?
That first part, we're under algebra,
I guess I'm just trying to understand where it starts off as I1 plus I3 equals I2. So that's the 12 volts minus.
So I pulled those.
Plugging everything in.
Yeah, I pulled those. So we developed those equations here first,
Yeah.
and I just wrote them down because this is the equations for electronics.
That's what it looks like cleaned up.
Yeah, and then over here it's like, okay, now we gotta do math.
Oh yeah.
So these three equations are this one, and this one, and I just simplified these two down and got rid of all the units so that they would be easier to work. And I'm gonna let you know, you need to be able to do this, but it's about as bad as it gets because then we have to come up with other ways to do this. We make the poor electrical engineers go through things where we do things like this, but we draw like 5 batteries and 10 resistors and make them come up with, 10 equations and 10 unknowns. But we don't do algebra. We put them in. If you've seen matrices and done something like Gaussian elimination and not matrices, you can actually do it pretty fast through that. But we won't. We'll move on to the networking theorems, which are ways to circumvent this and work it. Still takes some work, but we can do some tricks. So we'll come back and we'll solve this specific problem as an example, maybe not these numbers, but we'll come back and solve it using these various networking theorems. They're all ways to make this easier to solve. They all require some mathematics, no doubt. It's algebra, they're all algebra. There's a whole bunch of tricks to it. So when you look ahead, we can take this and we can go one step and we'll do what's called mesh current level, and we can make it a little simpler and just use 2 equations to solve everything. And then we can go do no low voltages, which will also produce 2 equations, just a different style to solve everything. And we'll move on from there. So that's kind of foreshadowing. It's like the middle part of the semester. Okay. I will leave all this up here. It's also all on video. Recorded everything. In fact, I'm going to shut the recording down.